All right. I'm going to give maybe a couple of minutes for people to join here. So, let me switch cameras. So, I've been working on some Rust lately for a project at work. Let's find it. Crustlet, which is kind of really interesting because it allows us to orchestrate WebAssembly uh, using Kubernetes as the API and everything. And so this is all written in Rust. So I've been doing some Rust development, and I mean, I'm not an expert at it. I'm still very much a beginner, but I really enjoy it over using things like C and C++. And so I've been a hobbyist electronics person for a couple of years. I've done some little projects and stuff like that. I'm still trying to get better at that as well. One of the things I created, let me see if I can find it over here, was this cobbled together craziness. And so what I use that for is actually a PID controller to control a blower motor that stokes a fire for a giant smoker that I have. And so I've been wanting to get back into embedded stuff because Brian and I did a project with Crustlet where I controlled like a robot arm. And so that got me kind of excited about doing embedded stuff. And I thought it might be fun to try to do Rust on the embedded devices instead. I still need to play with TinyGo a bit, but I think Rust will be a fun thing. So one thing I did come across was this online book on the rustembedded.org website, which looks like a tutorial for how to use, let me see if I got it here, to use Rust on one of these STM32 boards. I have a few devices stacked here. This is a teensy. I actually have cases of stuff. This is a smaller ARM device, a larger ARM device, and then a pocket chip. And I think all of these would be kind of cool to end up doing some Rust development on, but I think the best place to start is one that is well documented, and having this book I think is going to make things a little easier. So I think what I'm going to do over the next few days or week or so is try to make it through this book here to make sure that I don't mess up doing some Rust on embedded. And then what I'm going to do from there, hopefully, is maybe recreate that grill controller using Rust on one of these devices. And then if I can get all that working, I will try to start doing some WASM on one of these embedded devices. And then the big project would be to try to get Crustlet to run on one of these. Hey, Brian. This is right up your alley. Some Rust controlling barbecue controller eventually. Okay, so feel free to ask questions if you're not familiar with stuff, but I'm going to skip over some of this in the book just sort of because we know why we want to use a microcontroller. So why use Rust and not C? Well, there's a lot of things when it comes to security, but package management and all of these things are going to be pretty nice too. So let's skip to setting up our development environment. I'm currently on Windows. I may have to change that. I have not done embedded development on Windows, but from past experience, it seems like Windows is the place that has the most tooling, at least commercial tooling for doing embedded development. So I hope this all runs well. All right, so let's skip over to here and download our ARM toolchain. Is it telling us a specific one that we need? No. Okay. Wait. Add path to environment variable. Okay. Q2 update. Yes. This is us. Brian, do you miss Cupid? I can't believe it's been, what, 2 years? maybe even 3 years since we've worked on that. Oh, let me switch over to my desktop here. I'm just downloading inside this book. I'm just walking through the setup the development environment here. I need to get better about remembering to switch my cameras. Yeah, I'm talking about Cupid. It's talking about kind of, I actually have it right here. You joined a little late, but here's one of my prototypes with all the thermocouple amplifiers and a little teensy, and this is my Bluetooth device here. But yeah, I was talking about kind of redoing it using Rust on one of these STM32 boards, and then I was mentioning the fact that I kind of miss doing Cupid, and I can't believe it's been 2 or 3 years since we last worked on it. All right. We need some music. Let's see. What do we got? No. I am the most clutch player. There we go. Rock. Am I even going to be able to hear this? Probably not. You all can probably hear it. Oh, I've got my audio through here. Let's see. It's like 8-bit. Oh. I'll play with that later. I tried setting up this royalty-free music player so that if I'm doing this for a lot of hours, that we can do that. Let's see. It should be. All right, let's see what else we need to install while we're waiting for that. And we need OpenOCD. So this is an open source debugger that I've used in the past from Linux to be able to debug using things like JTAG and things like that. If you're not familiar with some of the like embedded terms and things like that, please feel free to ask questions. What is this? It's an official binary release for Windows, but there are unofficial releases. Let's see, which one does it say to grab? That's done. Linux, Win32, x64 zip. I'm really surprised OpenOCD isn't available for Windows directly. All right. I guess we need to add this to our path somewhere. Okay. We're just going to drop it in my C drive. And with any luck, this is going to work out the gate. I hope. Do I have putty? I apparently don't have putty. All right, and we're gonna need this USB driver. So there's there are these programmers that you can use to program a lot of these devices, and the STM32 has one called the ST-Link, and I actually have one of the physical devices here. I will grab it. Let's see. In my bin of stuff here. So unplug that. So this is one of the physical ST-Link devices that you can use to program these ARM devices that ST Microelectronics releases. So inside of the board itself, though, you'll actually notice there are two USB connections. One of them is, here, I'll show it a little bigger. So the one of them that you see plugged in is actually the built-in ST-Link here. And then this one is for our own use that we could program. Okay, so let's add, but with the drive letter that makes sense to you, then update your path environment variable. All right. Environment variables and path. And let's create a new one. C open OCD bin. Okay. I'm multitasking. All right, download putty. So does anybody here do any embedded development or Rust? All right, putty. Guess we're gonna do our serial communication there. You tinker with some embedded stuff too, Brian. You've got some Raspberry Pis all wired up. I've seen them. All right. Good software. I don't know what I'm doing. And I do. Let's see. Oh, this is gonna make me sign up. All right. Oh, I gotta check my email. Of course I do. All right, hold on. All right, let me close that out. Oh, I'm not even showing you my desktop. Okay. But I don't know what I'm doing. Aaron says same. One of us is streaming, one of us is watching. Well, you're watching me learn to some degree. I can do some basic stuff on embedded. I'm a little rusty, but I am a long way away from being an embedded developer. I would not apply for a job doing it, I suppose. It would be a cool job if somebody were willing to pay me to learn on the fly. Okay, where'd we go? Now we need to install this. Nope, that's not what I wanted. No, we want AMD64. I always forget how long it takes to install stuff too. I was tempted to install all of this before I started streaming, but then I considered it might make for a better stream if other people are beginners and just kind of getting started and wanting to understand what all of these things are for. Okay, so we have our on-chip debugger tool installed. We have our STM32 library installed so that we can talk to the device and flash it. And then we have our ARM toolchain for building. Okay. Well, this is also GDB, which OpenOCD uses under the hood. All right. Meet our hardware. So we already kind of showed this off. I've got one of these STM32 F3 discoveries. So the F3 is significant because that is the ARM Cortex M3 microcontroller that's on there. So ARM actually designs the chips but does not manufacture the chips. So in this particular case, this is ST Microelectronics implementation of this ARM specification. On here, we've got a whole bunch of pins, but we also have some interesting things. So we've got a couple of buttons that we can make use of. We have an accelerometer. If you're not familiar with what an accelerometer is it will be able to detect when we are, let me just grab, this is not the device we're using. You can see that one on camera, but this one is an STM32F0, which is a sibling. So if we have the device, an accelerometer is going to be able to tell us which way we're moving. And then the gyroscope is going to be able to detect how much force we're rotating in any direction. And now that I'm making a mess of my desk here. Okay. What kind of device is this? So this that you see, this is an STM32 F3 discovery board. So in my hands here, let me just, I have an F0 discovery board. These are actually meant for developers who are trying to develop prototypes of these ARM platforms. So they often come with these STM calls them discovery boards, but other places will call them developer boards. And they often have like little buttons and LEDs and things like that that you can make use of for kind of initial prototypes. So the one that we're working with, the one that you see in the browser here and in the camera over here, is the STM32 F3 discovery. I bought one of those specifically so that I knew that the code that I'm using would work for a first pass, especially because I haven't done embedded stuff in a little bit, and I'm fairly new to Rust, and I know that the embedded stuff in Rust is still kind of progressing, so I figured let's go with something I know works, and then we can use that as reference when we move to one that it doesn't. Does that answer your question? Okay. So, blah, blah, blah. We don't need a serial controller. Brian, you probably recognize this from your house. This is how USB can talk over a serial connection to the chip. And we don't need a Bluetooth module because it has one built in. All right, LED roulette. Do we get to write some code? All right. High-level API to implement this app, but don't worry. So for anybody who is just joining, what we are doing is we are working through the Rust embedded book that is dedicated to the STM32 discovery board. There's actually two embedded books. One of them is, it expects that you have experience in Rust and in embedded development. So I figured this is probably a better place to start, especially because there's some interesting things about the way Rust is done for embedded, because we don't want to include the standard library and things like that just because we don't want any runtime code because it can't fit in the small amounts of memory. What are we eyeing? I missed something. Okay. So, main goal of this chapter is get familiar with the flashing and debugging process. Throughout S6, we'll be using the starter code that's in the discovery repository. Make sure you always have the latest version. Okay, so let's go get this. All right, and we want to clone this. And then I guess we're going to do this all in Windows, so that's PowerShell. And we're going to go into code. Nope. So no, it doesn't have the it doesn't have a special compiler for embedded. As you kind of saw in this here, have sort of like these macros to tell the compiler not to include the standard library and not to include all of the logic for main. And then this is a macro to sort of tell it where the entry point is going to be. And Aaron, I know you kind of have experience with Go, so I'll use this as a reference. Underneath the hood, Go does it has a runtime that's kind of controlling which CPUs or threads Go routines and things like that are being scheduled on. So that in itself is a bunch of code, as well as requires a bunch of memory to do. So what we're doing here is we're telling the compiler that we don't want any of that. We're going to control everything ourselves. We don't want the extra cruft. All right, so did we get that? Let's bump up the font a little bit on this. All right, so this wants us to, there are more directories named after each chapter. Most of the directories are start go, blah, blah, blah. Now jump chapter 5. All right, let's open this in VS Code. There we go. Yeah, that is super handy that you just have to kind of add this little macro to say, hey, please don't do that for me. It's basically your way of telling the Rust compiler to hold your beer. Okay, so here is this project, and under source, we'll look at main.rust. So this is us. So what is aux5? Y equals axis. So we're looping here, but I don't see it doing anything. So no standard attribute. This program won't use a standard crate, which assumes an underlying OS. The program will instead use the core crate. And I've seen that as well, some references to it anyway. We won't use the standard main interface, which is tailored for command line applications that receive arguments. Instead of standard main, we'll use the entry attribute from the Cortex MRT crate. And there are some crates specific to individual chipsets too. So you kind of have to search around for those, and in some cases implement your own if you're using a microcontroller that somebody has not written one for yet. And let's see if we can pull this up. Yeah. So, which is one of the reasons why I wanted to start with this. All right, and functions must have a signature function. This type indicates that the function can't return. This means that the program never terminates. Okay. If you're a careful observer, you'll also notice that there is .cargo directory in the cargo projects as well. The directory contains the cargo configuration. Okay, that tweaks the linking process to tailor the memory layout of the program. So let's see if we actually have one of the linking files. because you typically have a linker file that tells the compiler where in memory the flash is, so that it knows where to write it. Okay, and we'll find that here in a bit. Let's move on. I want to see roulette going. Okay, the first step to build our binary crate, because the microcontroller has a different architecture. Simple passing an extra target flag to Rust C or cargo. The complicated part is figuring out the argument of that flag, the name of the target. Okay, so we have an M3, so this is us. Oh no, we're here. M4. Okay. So let's see if we can compile this. Ooh, that's not good. Rust up, the term rust up is not recognized. It's the name of a commandlet. Ooh, so we don't have Rust installed. We don't have Rust installed on Windows here. Did I only do that? I bet you I did this before I reloaded my computer. Oh. Keep anyway. What kind of experience does everybody have with Rust? Is anybody here a seasoned Rust developer? Where did that install go? No Rust yet? Yeah, I've been having a lot of fun with Rust. I mean, I've run into a couple of interesting scenarios where I've been trying to work around kind of the way Rust requires you to write code. And it's interesting because on one hand you get kind of frustrated by it, and on the other hand you're like, well, really they're right, you shouldn't write code that way. But I like the ownership model of it. And I mean, in particular for doing embedded stuff, it has a lot more appeal to me than doing C and C++. Becoming experienced, though not seasoned yet. Yeah, I can get around in Rust, but I wouldn't call myself seasoned either. But all right, why is that not working? I know we just installed that. What did I miss? I know it's in here. There we go. Now I probably need to, yeah, I'm gonna need to close that and then open a new one. Yeah, Ryan streams are really awesome. I'm gonna have to pick his brain sometime too. Is not recognized as the name of a commandlet, but we just did that. Rust up. Ah. Let's just do it from here. I think this just hasn't reloaded my path information. Maybe if we close out of code, we'll try that. And interestingly, I'm just now getting proficient moving around windows too, because I've primarily been a Linux developer. There we go. Did that compile? Slash target. Let's see. Where did you go? All right, let's take a look. All right, so we've compiled it. Oh, we added the target. That's what we did. Okay. And now we can build it. Yeah, good catch. Oh, oops. And this was discovery. We want this one. Okay. Let's go ahead and copy this. We're going to look at. It's kind of cool that Cargo has a read object built into it too. I didn't know that was in there. This download should take a lot less time. I've got a gig connection going both ways. This thing should be like instant. Jay Vega, do you do any embedded development with Rust? All right, there we go. Now let's see. No such subcommand, read object. So what are we missing? Yeah, that was sort of my thing too. I've been doing some Rust development and I've done some embedded stuff in the past. So I figured this might be a fun way to mix the two. Let's Google this because Cargo. External tools. That's not what we were looking for. I may skip this too, but cargo bin utils. Okay. Cargo install. This step is missing from the book. Okay. Build, I want to see this. Is that Windows development? It is Windows development. I'm trying to dog food here. I mostly do WSL. But I do know that from prior experience doing embedded stuff, there actually is really good tooling for embedded development on Windows. So I'm attempting to see whether I can do it straight Windows, especially because I need to communicate with the USB device directly to program the microcontroller and stuff. So I figured it might be easier. Although I suppose is something that we could work towards is I could try to see whether I can communicate with it over WSL too. All right. What do we got? The system cannot find the file specified. Where did it spit the file out? Oh, it's under here. So it's under target thumb. Oops. Aaron said it didn't used to be possible on WSL. Have to check into whether that's changed. Yeah, I mean, that's a... All right, so let's double check. So we have... so we have the right target, so why is it not finding that? Do we have to give it the directory? No. Something we've used in other scenarios. Let's skip this real quick. I will debug that here in a second. I want to see something running on this board. It's built. All right. Persistent memory, once flashed, the microcontroller will execute. In this case, the LED roulette program will be the only program in the microcontroller. By this, I mean... Oh, so this is actually really kind of cool because it starts from a standpoint of like if you don't have embedded knowledge. Okay, well, onto the flashing. First thing we need to do is launch OpenOCD. We did that in the previous section, but this time we'll run the command inside a temporary directory. All right. Let's just cd into. Yeah. Why can't we cd into that? Here's where I become Windows dumb. Do we not have a temp directory? Interesting. All right. I'm gonna try something. What? So that works. I guess it just doesn't work under PowerShell? Okay. Wait a second. We need to get... So underneath the OpenOCD directory, let's go find it. We have... Because it's going to be under share. Oh, that's docs. Scripts. Scripts. Target. So this is where these config files are. So we just have to update this this command to look for it there. So we need OpenOCD / scripts / term -f is not recognized as the name of a commandlet. Does PowerShell allow for multi-line? That is a very good question. Let's try and put this on one line and see. I'm not much of a PowerShell person. I think that's why it's yelling at us, is because it thinks that's a different command. All right. Yep, okay. So what do we got? Interlink ST-Link v2 is deprecated. Please switch to ST-Link config. Okay. Open failed. I'll select the first available session transfer. Took overload. Open failed. Multi-line in PowerShell via backtick, I think. That's an interesting choice. Okay, so let's see. We failed to open. Let's see whether the device shows up under the device manager. Let's see. What would you be under? This would be one of those things where I sit here and I spend an hour trying to figure out how to get the device to flash. That's happened multiple times, even through Linux. Let's see, where are you? Is it this? No. Yeah. By type. Keyboards. Yeah, I Let's see it. Whole bunch of Xeons. Yeah. So, this is a good question. So we were plugged into the ST-Link. Let's just unplug it really quick and see whether it gets recognized now that there's a driver installed. It's possible we don't have the drivers. We installed them. Let's see. Let's just go ahead and try and install them again. All right, let's see. This is the part that becomes not fun, I think. Took over the level target. ST-Link has their own tool. Let's look for that. We have one of those. All right, so that's the driver. Let's download the utility and see whether that finds it. I want to get to the fun part where we put code on the board. All right, let's see. Finish. All right, now let's see. No ST-Link detected. So if that's the case, our issue is that we're getting power from this USB device, but it's not actually connected to the computer. Do I have another? I think I might have another USB cable here that I could swap it out with. Give me 2 seconds. that's an adapter. All right, I grabbed a pile of cables. One of you is bound to work. That's our ST link. Let's see. All right. We're going to have to turn this camera, though. And I don't believe that comm light was on before. So we're making progress. There's a light right here that says comm on it that I don't believe was on before. So I think that may have been our issue. Let's see. There we go. We have an STM32 connected. So that cable that I'm using must be a power only cable. All right. Now let's see if it'll flash. And we are now connected to the JTAG setup on the board, and we have GDB connection open so that we can connect to it. So let's close that out. All right. So this is going to explain what it's doing. So it has two microcontrollers. One of them is used as a programmer debugger. We talked about that ST-Link that's built in. So it's connected to the target microcontroller using a serial wire debug interface. The SWD interface can be used to flash and debug. We talked about that. It'll appear as a USB device. Okay, so OpenOCD opens a GDB server, and that's what these config files are for. So this tells it, if we looked at this file, we close that. So I talked about where the linker is. Where is this? OpenOCD, scripts, target, and then if we look at this STM32F3X here, STM32F3X, we just open this in code, we can see this is setting some stuff up for JTAG. And where's the flash file? And you configure each of these for your own chip. Where is our flash information? No. And this is for the individual, so if we were connecting to a Raspberry Pi or things like that. So, okay. All right, let's see if we can get this thing running on here now. We've got it running in the background for the GDB server. So okay. So this is where we're going to take GDB. And is that installed? I think it was installed. GDB is not installed on here. Oh wait, we need our ARM none. ARM none. There we go. Okay, so now couldn't determine the path. So almost there. Okay. So what we've done here is we've loaded the program up into GDB. GDB is connected to the GDB server, that is being provided to us by OpenOCD over the ST link to this board. So now if we load this, no executable file. Oh, because we need to go backwards. There we go. Now we've got the symbols loaded. Now we can load this. Can't do that when your target is exec. Can't do that when our target is exec. Why not? What am I saying? Can't do that while our target is exec. Why are you giving me that error? Let's open up that PowerShell. What do we end up loading up? Target, Can't do that when our target is exec. Why? All right, let's Google that. Use the show GNU target. File format GNU target is set to read. Oops. GNU show target. No. Show GNU target. BFD target is auto. Oh, so is this not connected to? So this is not connected to. Okay, so it's been a while since I've done GDB work. So what this sounds like to me is that GDB is just starting up. However, it's not connected to the GDB server that is running on our device. And that is the issue that we are getting. So, oh, because we missed a step. That's why we read all of the documentation. Target remote. Okay, so now we're going to connect to the one that's running on OpenOCD. Then we should be able to load. Okay. We have just programmed it. Now we get to debug it. All right, so we're already inside a debugging session with GDB connected. So now we can set a breakpoint at main, and then we can continue. Okay. So now we have hit our breakpoint at main, and then let's make this bigger because oops. Layout source, yeah. So we don't get layout in here? Boo. This has got to be just from this particular version. So this has like a text user interface where we should be able to see the source code. I'll have to look to see why that's not there. I don't want to take up too much time because I want to try and do some stuff. Now, as far as cool text user interfaces, this is one of the coolest projects I've ever seen. Radar. And all of this is, you can use just key bindings and stuff like that, similar to like Vim to move around. That's just a GUI that's put in front of it, but yeah. This is for disassembly if you want to kind of do disassembling programs and following control flow and things like that. But their text user interface is really sweet. Okay, so I guess we're going to skip over this because apparently Windows GDB does not have that feature, which is kind of lame, but so this would allow us to step. Okay. Step. Oops. Step. Okay. Oh, and if we want to print the values of these things too, we can do that. So this is just sort of debugging. So we're going to print what X is set at. If we do $X, then we're going to, not $X, and reference, $X. That's going to give us the address and the type. Oh, this is nice. It actually shows us what the Rust type is. Okay. And that's just printing other stuff. Okay. Oh yeah, if we do info locals, we can see all of the local variables for this particular stack frame. Ooh. Oh, it's not going to give me this layout either. Let's see. GDB Windows layout. Let's see. Yeah, I think this is all going to be Linux. I'll look into this off air, just so that, because I think long term we're going to want that. And in fact, Radar has a GDB interface to it too, so maybe I'll play with that too and see whether I can get that working, because that would be even better. I'll probably drop here soon. I've got another meeting I've got to get on, but yeah, maybe I'll jump back on tonight. Okay, so back in main, we can quit, don't close, blah, blah, blah. Okay, so I've got two high-level abstractions that we use to implement the LED roulette application. aux5 exposes an initialization function called init. When called, this function returns two values packed in a tuple, a delay value, and LED's value. Delay can be used to block your program for a specified amount of milliseconds. LEDs is actually an array of 8 LEDs. Each LED represents one of the LEDs on the F3 board and exposes two methods on and off, which can be used to turn the LED on or off. Okay, so subtractions, modify the starter code to look like this. Okay. Let's first quit this. Quit. Okay. Now, where's our code? Okay, so we're calling init. We're getting our delays and LEDs. They're mutable. So half period. U16. So I'm guessing this is half a second, 500 milliseconds. Then we're setting LED 0 to on, waiting, setting to off, waiting, and looping forever. Okay. That makes sense. And so now we're going to cargo build this. I wonder if there's a way to just save the target so that you can just do cargo build without having to specify the target every time. Build. I've got meetings here coming up. If anybody's interested later this evening, like, 7 p.m. Eastern or something like that, I can totally get back on and, oh, this is probably complaining about this. I can get back on and try to make it further through this. There we go. Okay, so we have built. Brian says I'm not leaving until that crap blinks. Well, unfortunately, I have some stuff I have to do, but we can get this part finished, and then I have some stuff going on, but I am totally, like, we can get all the way down here to doing Bluetooth later if we want. I'll just get on tonight and stream until, as far as I can make it, until I fall asleep on camera or we make it through the book. Okay, so we've already got our GDB running. Oh wait, no, we need, okay, and then we want to remote, wait, right, target remote. Wow, I am rusty with GDB. Okay, load. All right, and break main. Continue. Why didn't we? That's interesting. Kill it. Start address. Interesting. That compiled, right? Finished. These are all just warnings. So why did it not get our new code? Let's oh. Um, hmm. I feel like that's not loading our code correctly. We did build it, that target. Uh-huh. So let's see. It says this one runs a debug session for us, which could be interesting. You go away. I'll have to play with that later. Why are you not working? I'm gonna rebuild this. Oh no, it's under here. Let's see. I didn't even see it under there. Target, thumb, LED roulette. What am I missing here? It should be under here. Why is it not showing up? Where are you? That's showing just the debug directory. I'm confused. Yeah, so it's not there. Yeah, so I did read on here where it was saying cargo run will build and start a debug session. So that's what I was toying with, but that didn't appear to work. So what it looks like to me is that this didn't actually compile because that directory is empty. So that seems to be our bigger issue, is that, oh, this is why. Because I did the cargo build from the top level and not from the actual project. You gotta love that it doesn't matter how long you've been a programmer for, you make silly mistakes like this. Ah. And I wonder if that is also why that cargo run was not working the way I expected it to. Okay. Now I'm willing to bet that there's stuff there. And there's not. Is it failing? It's saying it finished. Cargo build. Slash target. Why are we not building? There are no errors here. Yeah, that's all we did before was just that cargo build. So it's got to be something with our code here. All right. No. So what did we mess up? Now this is strange because we built all of this code before. We're getting no errors. We're setting our target, but yet we don't get anything here. I am confused. Let's... Yeah. Lag, what's lagging? The video feed? I am extremely confused why this is not building anything. Because we have no changes. We are running the same build, which is saying that it worked correctly. Oh yeah, so I intentionally put the chat there so that everybody can see it later, and also so you can kind of get a feel for whether or not I've seen your message. Anybody have any ideas? Because this seems like just a Rust issue. Why, when I run a cargo build, would it not produce anything? Oh, sweet. Yeah, all right. Let's get rid of that. Cargo run worked. Okay, so now we need to put our code back. Can we redo everything? No. All right, let's go back and get the code. Here. So it looks like that cargo run thing did actually do exactly what we expected it to. So in theory, there's our GDB. And now we want to, all right. Oh, this is just having a C bug. Okay, so next we want to set our target to our remote OpenOCD instance. All right, Brian, I'll be back on later. I'm going to be calling it quits here soon too, and then I'll jump back on later. All right, so we're going to set a breakpoint at main. There we go. I need to look into that. All right, so let's continue. All right, we are inspecting our local variables. Okay, and this is just stepping through next. Next. Oh, we have our blinking LED. Oh, and we halted. Interesting. Let's see. Did I close OpenOCD on accident? Yeah, I did. I was thinking that was GDB. Oops. All right. Ooh. Continue. Next. Yeah, we're halting. Okay, so info on. Okay. Well, we can also do that too. So let's get a backtrace really quick. I'm just gonna show that off. Oof. Yeah, we might want to do this in another terminal where we can kind of see this. I like that it's color coded in here. That's kind of cool. So, well, we have blinking LED, right? No, because we halted. So, oops, that's not what we want. Run. Oh, target. I keep forgetting to do this. So you can actually set a config so that when you open this, it will automatically set the remote for you, which we probably should do for long term. All right. So, okay. All right, and there's our blinking light from this code. It is about 3 p.m. here, Eastern time. So I think this is a good place to stop. We have our blinking light. I've got some meetings and stuff I have to jump on, but I will probably be back online later this evening to see whether I can make it through more of this if anybody wants to play along some more. And hopefully I can also look into why I can't see the source code layout and stuff through GDB on Windows. All right, well, thanks everybody for jumping on, and I'll be back on later. And once we make it through all of this, I'm going to try and come up with a cool project that we can kind of develop from start to finish. And I'll have to figure out a camera layout for over here at my electronics desk so that we can do some soldering and stuff too. Did anybody have any questions about any of this stuff before I called it for the day? Well, thank you for joining. If you're bored later this evening, I will be continuing along with all of this, and this will get into some more interesting things too, like registers and things like that on the microcontroller. If you're new to that sort of thing, learning about I2C and some of these serial communications like USART and things like that, it's actually really fun to learn about. And I learned so much more about programming and hardware when I started messing with microcontrollers and needing to understand that stuff at that level. You know, we take for granted a lot of things like time, right? If we say sleep, well, how does it actually manage to know how much time has passed? And you're actually counting CPU ticks, and when you're doing it on microcontrollers, you're doing divisions of the CPU frequency to figure out how much time has passed. And then you have like interrupts you have to account for. When we think about race conditions in programming, it becomes even more interesting because at the hardware level, you don't know if there was a hardware interrupt. So in between two lines of code inside a function that you have on your embedded device, you could actually receive a hardware interrupt. And so yeah, even check and set type things can become problematic for race conditions. So that'll be some fun stuff that we'll run into as well. All right, so we didn't make it as far as I wanted to. We kind of had some delays with getting started and debugging, but I will jump back on here in a few hours and see how much further we can make it. If you can join and play along, awesome. I will see you in a few hours. If you can't, all of this will be recorded. I'll archive it to YouTube too, so that if you don't get a chance to see it before Twitch decides that it's no longer valuable to them. Thanks everybody for joining. I'll see you in a little bit.